Hello. So last tutorial that we did, we focused on points within polygons, right? So we're comparing the campus trees to a fishnet of polygons that we had created. Today's tutorial, we're going to kind of expand a bunch on that. We're still going to be looking within polygons, but we're going to think about not only points, so we'll revisit the points again, but also lines, polygons, and raster data within those. So that's sort of 4 separate pieces to work on. That's going to be a lot in this single video. So feel free to break it down, into the 4 component parts, work on the points first, work on the lines some other time, polygons, and then raster, right? So yeah, so lots of content today, which is fun. All right, so we're looking at, and again, I'm working in ArcPro, but you can do all of these same processes in ArcGIS desktop. We are looking at a bunch of watersheds in Massachusetts, just sort of a random selection of watersheds. We can open these up and see that in this case, there's not too much going on with these watersheds. All we have is a name of the watershed. So one nice thing to start out with is, okay, these watersheds, unlike the fishnets, which we created ourselves, right? The watersheds come with a unique identifier, or what looks like a unique identifier anyway. We can double check that it's a unique identifier by summarizing it and seeing if the sort of count of each individual name is the same as, should equal 1, basically. Let's just do a count. So basically, I'm just double checking that there aren't duplicates in this field called name, and there are 182 different rows here. If there are no duplicates, then this summary should also have 182 rows and everything should have a frequency of 1. So that's good. That tells us that there aren't any duplicates within this. I'm just going to delete this because I don't need it anymore. So these are all each unique identifiers, and we can, go around and, go around and look for, that's not what I wanted, for where each of these basins are located. These must be some small ones. So there we go, all these different ones, as you would expect with the spatial layers. I have given you dams in Massachusetts. So here is a data set of locations of dams. Some of those are inside the polygon, some of them are outside these watershed polygons. So you should, at this point, be have a pretty clear process in your head for how to count up the number of dams in each of these watersheds. But let's go ahead and go through that quickly, right? If we want to know, let's open our dams. If we want to know where these dams are located relative to those different watersheds, then what we need to be able to do is to pull that unique attribute information about the watersheds into and associate it with each of these different points, right? So that is our spatial join. And our target features, the one where we want the information to end up, is our dams. We want to add to it our basin information, and none of this is all that important when it's points because they're all going to be the same. All of these different options are going to be the same, completely contains, within, intersect, etc. So off we go. Now, the main thing that we should be expecting here is that in our Massachusetts dams, once this finishes processing, we should have an additional field at the end that, let's see, I guess in this one, in our new spatial join layer, that has information about the name of the watershed. Now there's a bunch of nulls in here, and that is to be expected because there are points, because our watershed, remember, is not the entirety of the state. It's only some portions inside of it. So there are a bunch of points that are outside of those watersheds. And we don't care too much about those because all that we care about are the ones that are inside the watersheds to count those up. How do we count those? We use our handy summarize tool based on lots of fields in this data set, based on the count of all of these names being the name of the watershed. And this is just an error telling us that there were some null values in here and GIS ignored them, which is fine because, you know, there were 1,000 points, 1,063 points with null values that, you know, we don't really care about in this case. We just care about the ones that actually fall within the watersheds. So it turns out there were only 82. Oh no, never mind. 82 is the number of watersheds. I don't know what I'm talking about. I think we started out with 1,500 was the number of points that 1,500 dams, so 1,063. So we're left with whatever that is, 437 dams that are actually inside one of these watersheds. If we want that information back to the watershed so that we can display it and count up how many are in there, that's where we do our regular old join, name to name. I should have renamed this earlier, but I'm being lazy today. All right, so now when I open my basins attribute table, I should find a frequency and a count, which are the same thing, right? Because summarize automatically does frequency, so count is redundant, but won't let you go unless you do that. So I'm going to add a field to this, and I'm going to call it count. Yeah. Good. And I'm going to copy over with my field calculator that information about either the frequency or the count name would be totally fine. Let's go with frequency, it's on top. And then we end up with zeros for places where it was null, which is what we want, and numbers for everything else. So now I can release that join because I don't want all this extra junk that I'm not using in my table, clean it up. And now this means that, let's turn this off. As you would expect, now we can summarize. Trying to like pull this down, there we go. We should now be able to not summarize, symbolize our basin study area using, let's go with graduated colors because we've got a number low to high. And it's automatically choosing the counts of dams because that's the only number value in here. And I'm not so sure about that particular graduated color. I feel like maybe this one is a little bit more intuitive in terms of a light to dark, where the light ones are areas where there were 0 or 1 dams, and then as you get darker, you see the watersheds that have a whole lot more dams. You can also, so you could normalize this just as another form of symbology. If we were to normalize it, we would need an area is typically what you would normalize by. So let's call this area in square kilometers. It's a long integer, okay. Let's change this to floating point just so we've got more precision. And so we can calculate the geometry of that. And I want that to be area. Does it not let me use, oh, it does let me choose a unit. That's fun. Area in square kilometers, because I told myself it was going to be the area in square kilometers. And hopefully we can, actually not sure. I think that Massachusetts dams is, okay, so that's in Mass State Plain. Shouldn't matter what the coordinate system is as long as there's some sort of coordinate system defined and GIS can handle doing square kilometers. I don't think you even need to check anything there. So if we had an area, so just a little bit of a tangent, but if, for example, this tells you the total number of dams, but you can see like this watershed is pretty big compared to this watershed, which both have a lot of dams in them. So maybe instead what you actually want to display is dams per square kilometer of watershed, in which case you can do the normalization and then you get a slightly different picture of what this looks like, actually, because this one is so tiny, you end up with large concentration of dams per square kilometer. So depends what you're trying to visualize. Okay, so that's our points. All of that should have looked pretty familiar in terms of stuff that you've seen and done before. Next, let's think about roads. So roads are a line file, right? This is actually the census roads layer. So that's why it's taking a little chunk to draw here. There are a lot, there's really fine articulation, like every single road in the state, at least as of 2010, should be in this data set. So lots of roads in here. Let us zoom in a little bit so that we can see the roads and kind of see the basins behind them. Okay, so I want to ask the question of, all right, we've counted up the dams in each of these watersheds. Now I want to know what's the total length of roads within each of these watersheds, right? And typically, if you're combining lines with polygons or combining polygons with polygons, should start with the lines first. Typically, if you're combining lines with polygons, length is a question that you want to ask. I mean, you might have, there may also be plenty of cases where you have, individual line segments and you want to count them, but length is a pretty typical thing that you might want to ask when you've got a line file. Similarly, when you've got a polygon file, area is something that you typically might want to ask when comparing polygons to polygons. So let's start with that length of roads. We'll get to polygons later. So this is the line to polygon segment of the tutorial. First thing is that if we, so just like we did with the points, if we want to summarize the total length of roads in each of these things, we need to get that basin name into our road file. So we've got to do sort of the exact same process, or not exactly, keep contradicting myself, not exactly the same process, but nearly the same process. What's different about this one is that if I go in and I look at one of these roads and I click on this road, then I can kind of see that this particular road extends. All right, well, that's giving me some corner of it. I'm not quite clicking on the road. There are like these segments of roads. Okay, there we go. So this road is in the watershed. It's in whatever this watershed is, WT187, but it's also outside of the watershed, right? It's over here and it's quite a ways over there. If we did a spatial join, then we could add the information about this watershed to this line segment, but it would also include this chunk, over here. And what if this road went into another watershed? Then we start ending up with kind of a mess, basically, in terms of where this information gets appended. You end up with like more rows than you started out with. Which means that, so I prefer, in this case, to use an intersect instead. So an intersect, you might remember, oops, find me my intersect. Oh, look, it's right here. An intersect is one where, let's see if the help menu over here gives us a picture. Yes, I saw it. An intersect is one where you only keep the area that overlaps, right? The intersecting area between two features. So this is showing it for two polygons, but you could imagine that if there was a line going through this circle, then you would just end up with the line portion that is inside the circle. to move my head. And that's what we want, right? Because we only care about the length of the line segment that actually intersects this this watershed area. So our input features, the nice thing about intersect is that there's no order, so you don't have to guess about it. So we want our basin to come in, and we want our roads in Massachusetts to come in. And let's call this in Watersheds. We want to keep everything, all of the attributes in the join, so that we make sure that we've got, the name information, although these pieces are going to be confusing later on. So maybe, all right, not too many options there. Unlike spatial, so the nice thing about spatial join is you get to choose which of your fields come with you in the kind of joined result. Intersect, you just get everything. So we might end up with a partial mess later on. So we're gonna have to delete some stuff if we care that much, or want our intermediary data set to make sense to us later on. All right, so that intersect took a minute. So probably on your computer, it will also take a minute. But now we have an output of our roads that are inside the watersheds, which I think I want to make that look a little bit brighter just so we can see it. Definitely can see that. All right, hot pink roads. And you can see, if we zoom in, that these roads are just the parts that are inside the watersheds, right? We have turned off basically or removed all of the things that are outside the watersheds. And if we scroll around, we can also see that some watersheds have a few roads and some watersheds have a lot of roads in them. So, if we were looking at something like amount of impervious surface in these watersheds, that's going to be something that's relevant to the length of roads would be relevant to impervious surfaces. Okay, so I'm going to open my attribute table and let's take a look at what we've got. So the most important thing that we've got is the name of the watershed associated with each of these 88,000 road segments. So it gives you a sense of why it takes GIS, a minute or two to process that intersect, because there's lots of different files to work on. These pieces that came from, oops, that's not what I meant to do. These bits that came from the basin are not meaningful here. Really, the only things that we care about are the name of the basin and the length of the road. Now GIS has already, because this is in a geodatabase file, it has already calculated and updated the length of those roads. The one thing that we don't necessarily know is what the units are of these. The units of shape length, if you've got that in a geodatabase, are always going to be associated with your projection of that, of your data. So let's just check out what our projection is. So in this case, spatial reference tells us that we are in mass state plane and that the units here are meters. Linear units are meters. It's also there. Vertical units are meters. There's nothing vertical about these roads, but meters are what shape length is going to be. So this is a teeny tiny little road segment of 1/10 of a meter. These ones are slightly longer road segments of 600 meters and so on. Because I previously calculated the area of the basins in square kilometers, and I could have done that in square meters too, like it really doesn't matter. It's up to you what units you're using, but I prefer to stick with the same units throughout. So I am actually going to call this length in kilometers, and we'll add that to our field and then just give it, oops, don't want to have anything selected. Just remember, it only operates on the selected things. And let's just calculate the length of that. Length in kilometers. Cool. All right, that took a minute to calculate, and then I realized that I made a mistake when adding this field, which you can see over here, which is that I made it an integer, or I allowed the default to persist, which was probably a long integer. And when you've got an integer, you're going to round to the closest integer. So 0.347 kilometers rounded to 0, 0.652 rounded to 1. So let's fix that. I want to make this floating point instead. And I will have to delete this other one later on. Good enough for now though. All right, and since I remember that this takes a while, I will do that same thing and then we'll come back when it's done. Length, kilometers. All right, hopefully this one will work right. Right, so now we have actual length in kilometer in here, and I deleted the other fields so that I wouldn't get confused later on. Okay, so now we're off to summarizing, and here's where summarizing is going to be just a little bit different from what you did before, because rather than focusing on count, we actually want the sum of all of these things, right? We want to add up how many total kilometers there are within each of these watersheds. So we're summarizing by the basin name, but our statistics that we want, so basically the numbers that we want to generate, are going to be based on length in kilometers, and GIS by default is selecting the sum of these things. And in this case, so this is where things are going to be slightly different from the way that you've done things before. Now we do need a case field, right? So we want that case field to stick in here as name. It's coming in by default because that's the one that I clicked on. Let's call this lengths. We've got sum of length within each of our named watersheds. I think we've actually had that case field thread. I'm not sure what I was thinking just then. And it looks like it's here, so let's open that up. And now we can see that, and so just like we did with the points, we always by default end up with this frequency, which is the number in this case of road segments. It's not particularly meaningful because the way that the road segments are, you know, some of them are just like continuations of the same road as it crosses a town boundary or changes its name or what have you. So I don't care. I don't think that frequency is particularly useful, but this piece is pretty useful, right? So, you know, this watershed has 78 kilometers of road length. There are going to be some watersheds that have, you know, over 3,000 kilometers of road length, to some that don't have too much in the way of roads at all. So now we're going to bring this information into our basins, because ultimately to visualize these things, we want it all to end up in the polygon. So that means that we need to join from the polygon. Our join field is going to be that name, right? And I want to join the road lengths. Good. So now I'm going to do same process, that I've been doing, this whole time with my tables. I don't know why I can't scroll over to the right. I guess I can go this way. I've got this sum length kilometers, but again, I'm not going to remember that if I come back, a month from now, a year from now, that sum length kilometers is actually total road length in kilometers. So let us add a field that is called road length kilometers. Road RD length. No, good enough. Length in kilometers. And now I'm going to remember to make sure that this is a floating point because I want to keep all of my integers here. And just like we've done a few times before, we're going to use our field calculator to carry over that sum length in kilometers into, so it should be the same value here to here. And now I'm happy, so I'm going to release my join so I don't have to deal with these repetitive multiple fields, right? So cool, now I have the area of my basins, I've got the road length. I'm going to turn off these roads because road length was the main thing that I was looking for. So now, rather than visualizing dams per square kilometer, let's visualize road length in kilometers per square kilometer. And get rid of these guys. Go down. I have a real problem getting this table to be smaller without closing it. So I'll just close it. Okay, so now we can see, and this makes sense, right? So eastern part of the state has a lot more urban and suburban areas than the western part. And so we actually end up with this kind of interesting gradient of higher road density, moderate road density, and low road density as you go across the state in terms of roads. If we didn't normalize it, then the area of those different basins is going to influence things a fair bit, right? This is a really huge basin with a lot of road length, and so it ends up with lots of roads. So that's where that normalization can give you just a different picture of how things look, right? Again, this is a cartographic choice. It depends what you're trying to emphasize. Okay, so hopefully that's our sort of next segment of combining lengths, combining lines with polygons to get some information about the length or the total length of things in each of these polygons. So last up next up, because we're going to do raster too. Next up are polygons to polygons. So here I have this layer, which is interior forest, created by Mass GIS, and we can turn that on. I never like symbology with a black outline because I always feel like it makes it really hard to see things. So let's just make these like dark green with no outline, and then I think you can kind of see where the forest is a little bit more, right? So we're probably also with this particular layer going to end up with one of those gradients going from, the western part of the state to the eastern part of the state. But this piece also, if you're interested in kind of water quality or watershed, the amount of area of interior forest might be relevant for trying to understand something about that watershed, water quality. So we're going to do very similar process to what we just did with the lines, except in this case, we're going to do it with these polygons, right? So again, when we were dealing with the lines and they went across different watersheds or inside and outside a watershed, we used the intersect to just focus on or create a new data file that was only the lines inside each of those watersheds. We're going to do the exact same thing with these polygons, because in this case, what we want to know about is the total area of interior forest, right? Before we were focused on length, now we want area. Same process though. So we'll start with our intersect. Now I want it to be with my interior forest, and I want to call it forest in watersheds. Off we go. Okay, so that didn't take too long on my computer, just because there's actually fewer shapes of the interior forest than there were of the segments of roads. So that's why it takes a little bit less time. Forests and watersheds. Let us just change this to just that single symbol. But you can see the difference between these things. Because we use an intersect, remember all of those attributes get combined. So that's why we had not only the location of all of these forests, but also the name, the area, the road length, you know, other stuff going on in here in terms of information that came from the watersheds rather than the forest. So GIS decided for us to symbolize those based on, you know, the density of roads within each of those, but that is not useful in this case. So what we want now is to repeat that process that we did with roads. There is an area of square kilometers, but remember that this area of square kilometers came from the watersheds, right? So we have to be a little careful with what we name the field so that we summarize against the correct thing here. Still have our name. In this case, because we're in a geodatabase, like length isn't really meaningful for polygons usually, but area is a thing that we are interested in. So this is the area of all of these different individual polygons of interior forest within these segments within each of these watersheds. Again, what are the units of this? These are going to be in square meters because the projected coordinate system of Mass State Plane is in units of meters. So in a geodatabase, it's going to update it as square meters. Because I'm working in square kilometers today, I don't want my thing in square meters. I want it to be, and I'm going to call this forest square kilometers. The reason I'm doing that is because I want to differentiate it between area and square kilometers, that information that was just appended to this data layer from the watersheds. Forest area in square kilometers. And I want to make sure that I make that floating point so that I get more than just the integers. So just like we've done before, we are using our geometry calculator to calculate forest area in square kilometers as area in square kilometers. Like it. Okay, good. So there are 1 million square meters, 1,000 times 1,000. So 1 million square meters in a square kilometer. So if we move this over 6 decimal places, we should see this result. That's just going to make it easier for me later on if I want to normalize, you know, area of forest relative to area of basin, that we've got the same units. Okay, don't want this. I'm going to close that for now. Now I am back to my basins. I want to join up my name of my basins to the name of, in this case, oops, I'm a step ahead. Sorry, step ahead. First, we need to summarize this, right? And we want this to be called forests and watersheds. We'll just call it area. Case field is already there in terms of the name of the basin. And now we want forest area, and we want to add all those up again, just like we did with the road length. And that should give me this. And now I'm good. And I can do my join. Name to name, but the one that I want is called Forests and Watersheds Area. Okay. And I don't want this guy, but I do want to check out my attribute table here. Again, a bunch of gobbledygook going on over here. Apparently we've got at least one watershed with no interior forest in it. I'm going to add my field. Forests in square kilometers, right? I love the alias because you can write whatever you want in there. We want this floating point. Okay, and remember that the sum of our forests in kilometers is our interior forest area in square kilometers. So I'm just going to copy that over. Should be the same, looks the same, all well and good, and we remove those joins. And now we should have a clean looking data set with our area of interior forest, total road length in kilometers, and our area of the watershed in square kilometers, as well as our count of dams. So now I can, rather than looking at road length, I can instead do this in terms of area in square kilometers, forest area in square kilometers normalized by total area in square kilometers. And I suspect that we're going to see that same kind of gradient in this case in reverse, where you have higher density, basically, of forest per square kilometer in the western part of the state and lower density, but a couple of watersheds looking not too bad. Lower density of forests in the eastern part of the state. So basically the reverse of what we saw for that road density. All right, so there you have it in terms of polygons with other polygons, right? So the intersect is key when you're dealing with trying to just capture the length of roads or whatever length of lines and the area of polygons inside of some other polygon. You first need to intersect it so that you've just got the stuff that's inside. All right, good. So we are a good chunk of the way along. Let us next look at this wacky layer. All right, so this is our topography. This is, I believe, elevation in meters above sea level. So going from sea level, actually below sea level in somewhere, to 1,000 meters or thereabouts somewhere up here in Western Mass. Okay, so raster data sets we treat a little bit differently from vector data sets, right? So in this case, it is not going to be the geostatistics tools. So we can't intersect these things. We can't do a spatial join or anything like that because those only work between vector data sets. Now we need the tool that works vector polygon to raster. So take a second, see if you can remember the name of that tool while I grab a coffee. All right, so hopefully you thought about that for a second. The tool that we're looking for is something that's going to give us statistics or information about a raster grid that is overlapping with polygons. And that is called our Zonal Statistics tool. We want zonal statistics as a table because we do want the output of our zonal statistics. And I don't know what the difference between image analyst and spatial analyst is, but spatial analyst is what we usually use for raster. So let's go with that. Okay. So our input features zone data. So this says raster, but that's kind of confusing. So like you could use a raster grid, I guess, too, if you wanted here, but generally your input is the polygons. So that's our basin study area. Our zone field, remember, and this is important, so GIS is helpfully suggesting the correct one, but we want name to be the zone field because we want this information based on the name of each of the different watershed names, right? And then our input raster is our, this is a topography from the National Elevation data set. Let's call this topo in watersheds. Statistic type of all, if you're not sure like what you want, then all is good because you'll get everything. But you also have lots of options. So if you wanted the mean elevation within each of these watersheds, the majority, the one that happens the most often, the maximum, the medium, the minimum, blah, 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 on down this thing. So I'm kind of cool with all because then we can decide later which of these we actually want. So let's output that table. Cool, that didn't take too long. Let's see what it looks like. So we should find still our 182 watersheds, right? With all of that information. And then we have, so count in this case is going to be the number of pixels inside of that watershed. So it's going to be proportional to area. Area, I think here is weird, probably because this unit of area, I'm guessing that the projection here is a geographic coordinate system. And that, yeah, so it's a geographic coordinate system. So any units of area are basically not actually units of area because this is square decimal degrees. And again, because decimal degrees are a different length when you go east from when you go north, this is not a super meaningful unit. So we'll ignore those ones. I don't really care how many pixels there are. I already know the area of my basins, but minimum elevation, maximum elevation, range of elevation, mean elevation, all of those things, standard deviation, all of those are pretty useful, potentially useful pieces of information for understanding more about these watersheds. So we've got name, we've got all this lovely information that we want, just like we've done now a few times before. Let's bring it back into our basin information based on name, and I want to join to the topo in watersheds that I just created. Close this and open this guy. And now once again, we should have a bunch of additional information at the end. If you want all of this information, the fastest, rather than adding a dozen new fields and copying that over, the faster way to do this is just to export this data sheet as, basins, whatever it is, version 2. Oops, wrong. Put that here. because that should, I'm just going to double check what the coordinate system is. I want it to be the same as my basins, which should be my mass state plane. It would have done that automatically. I just wanted to double check. This one, this basins version 2, should automatically come in now with all of those additional fields attached to them, as long as you remember that min, max, range, blah, blah, blah is topography, not, you know, because max doesn't necessarily mean anything, but you can always, you know, like change the alias on change the alias on some of these, so you could make it min elevation, etc. on down here, so that you don't have to excuse me, so that you don't have to guess later on about what these things actually are, as long as we make all the fields wide enough so we can even see that. Cool. And then of course, you know, like if I think these are not useful, I'm just going to start deleting them. Zone code, not particularly useful. I don't need name twice. There is a there's a delete field tool someplace. If you have, you know, like a dozen things that you want to delete and you don't want to do it all by hand, then you could just say like this, get rid of all of them. So that's what I would do to clean this up. I'm actually going to go back to my original, I'm just going to remove this and pretend in this case that all that I wanted was mean elevation, so that I'm going to repeat the process that I did before. I always like to put units in my names because then I never have to wonder. All right, so I'm just gonna field calculate mean over to this guy. So that should be, oops, I see that I made that same mistake of accepting GIS as default again and chose the long integer rather than the floating point. I can, I'll fix it. Not be lazy here and actually make it correct. Mean. Okay, that's better. So if this was a case where that was the only one that I wanted, then I'm just going to do what I did before, remove all of my joins. And now I have my average elevation of each of these basins. So let's go back to our symbology. And now in this case, I can make it average elevation. That's not something where normalization makes sense, right? It's just like, you just want to know, is this high or is it low? You don't care about the area associated with it. So once again, just like our interior forest area, we've got a lot higher elevation as we go west into the Berkshires, getting towards lower coastal plain as we get out towards the Atlantic Ocean, which makes sense. Cool. So that was it. Those are the 4 pieces, right? The reminder of how to get point counts into polygons, how to get line length and polygon area into polygons, and now how to get basic statistics of a raster layer into those polygons. We did all of these for kind of a simple case scenario where each of these, we only had one type of line, just the roads. We only had one type of polygon, just the interior forest, and one type of, so the raster layer was a continuous one, low to high, as opposed to categorical. Dealing with categorical data is sort of another step on top of this. That's what you're going to do for the lab report, is deal with land cover data as both polygon land cover data and raster land cover data. So we'll go through in the next, we'll do another short tutorial for dealing with, for what to do when you've got not just a single interior forest, but all the types of land cover, and you're trying to understand information about those within the polygons. And same thing if you have a raster land cover data set. So more on that next time. Thanks, guys. See you in class.